resume for a bot. And that bot does not take much of a salary, does not take holidays, does not unionize. It's a very difficult time for all of us in terms of employment as well. So one of the things that we're not giving LLMs credit for is large language models automate interaction. Okay? Now, you see that restaurant robot? How many of you have seen that restaurant robot? That thing today, all it does is brings your orders. It's a matter of weeks before that thing can talk to you. It can take your order. It can say, I'm sorry, if you speak Chinese, I'll speak to you in Chinese. If you speak Tagalog, I'll speak to you in Tagalog. It's a matter of time before it says, I'm sorry, ma'am, you wanted pepperoni pizza. We're out of pepperoni. Will you have chicken satay pizza instead? And it's a matter of time once it brings your order before it can take your payment. Imagine the impact on jobs. Very special and scary time. Knowledge. One of the things that ChatGPT does is it integrates knowledge. You can ask it the history of Ulaanbaatar. You can ask it where Genghis Khan was born. In the same breath, you can ask it to solve a mathematics problem. Something called Project Strawberry just came out on ChatGPT. If you have not used it, use it. Because it's not just a large language model. It introspects, it thinks, it reasons. And then finally reasoning. These things were not supposed to reason, but they reason. And that is terrifying. And that's what Project Strawberry does. It reasons. I won't show you these two. I would have shown it to you if I had my laptop because they're my accounts. But this is Project Strawberry on the left. You can ask it a very profound question with a workflow and it'll do it. This thing is terrifying because the sort of jobs that assistants do, travel agents do, maybe even insurance agents, this thing is beginning to knock on their doors. This is the one on the left. The thing on the right is also very exciting. You're all statisticians, you're in the statistics world. It came out from Google about 2 days ago. It's called Illuminate, Google Illuminate. You can point it to an academic paper. For example, those are papers. Generative agents, interactive simulacra of human behavior. It will read the paper and describe it to you like a podcast, completely automatically. A new academic paper, it'll read it and turn it into a podcast. And when you're driving into work, you can listen to the podcast. What this means is, not only is AI here, but you're in a race where someone else is listening to that podcast when you're not. People have said AI will not take your jobs. People with AI will take your jobs. So our first step is to get up to speed. And for that, we need to understand the history. So let's look at the history of AI. You see, there's a reason that I was quite keen to speak at this conference on statistics. The history of AI is actually a history of three things. It's big data, big stats, and big vectors. And let me tell you how that plays out. Big data, big stats, big vectors. Those three trends have gone through a confluence. It's a historical confluence. And this is how they came together. It's like many rivers coming together. The first is the field of statistics. Statistics, I'll give you the history in a minute. Again, it's important to understand the history. Statistics is, taking census, calculating mortality rates, and so on. But then, in about the late 90s, early 2000s, a new field emerged called data engineering. I'll tell you what that is. If you don't know it, I'll go through it very quickly. And those two things merged to create what we then call data science. Data science as a profession is only about 15 years old, 20 years old, max. It only became a job category in about 2007. That's data science. Then another thing happened. Meanwhile, for 80 years, as we just discussed, 84 years, machine learning was being developed. And another crazy, beautiful thing happened called word embeddings, which I'll explain in a minute, text embeddings. And those three things converged, and now we are at modern generative AI. But the first stream in this confluence is actually statistics, your field. In fact, I think that statisticians should have owned this. They did not. But this is a massive reset, and I hope that the statistics community will wake up to it, because instinctively you're best prepared to take on this field. So data, sorry for the typo there. Where does the word data come from? It's a very interesting history, even the word data. The word data comes from a fact, a datum, which is Latin, datum. And that comes from Proto-Indo-European. So in fact, even in Malayu, you have words like data or dana, like dana, impact, give. The same fact, same origin. And in 1897, it became a collection of numerical facts. And then in about 1946, during the war, we were able to transmit data, and the modern sense started appearing. And then data processing in 1954 with IBM. And then database in 1962, and then data entry by 1970. So the word data is actually a very ancient word. It goes back about 2,300 years. Comes from datum. Okay? Where does the word statistics come from? Anyone? By the way, I got this. This is all from Etymology Online. Where does the word statistics come from? I'll tell you, and then I think you might be surprised. It comes from state. Statecraft, statesmanship, state, the state of Malaysia. Statistics comes from the desire, and actually not the word, but the history goes back to Babylon. So in Babylon, ancient Babylon, they invented the hexadecimal system. Base 12, base 60. That's why we have 60 seconds in a minute, 60 minutes in an hour. That's why we have 360 degrees in rotation. They invented it because it's highly divisible by 3, by 4, by 5, right? The decimal system is only divisible by 2 and 5, but we have 10 fingers. So then the decimal system took off. The placeholder system from India, from Arabia, went to Europe. Actually, Southeast Asia used it. But the word state, statistics comes from state, comes from statecraft, census taking. So the first statisticians worked for the state. And they were calculating taxes, revenues, things like that. In fact, B&M, in many respects, is the ultimate inheritor of what statistics, where it comes from. And then probability theory took off. You know these names, Pascal, Fermat, Bernoulli, de Morey. De Morey is also worked in optics. And then pre-modern statistics. You know these names, Gauss, like the Gaussian, Nightingale, Pearson, Fisher. By the way, the Fisher here is the son of the original Fisher. Sorry, the Pearson here is the son of the original Pearson, Egon Pearson. Bayes, like Bayesian theory, right? And all of that plays also into machine learning, by the way. And then von Neumann. Von Neumann is this amazing Hungarian who came to the US and played a part in everything from statistics to computers. Just one of the most brilliant human beings ever. At Princeton, at the Institute for Advanced Studies. And then Tukey. Tukey, some of you may know, if you know the fast Fourier transform algorithm, Tukey was the inventor. Cooley Tukey. Cooley was the other one. And then modern statistics, which is Egon Pearson. Now, Bayesian analysis is actually, all it's saying is it's using Bayes' theorems from the 1850s, Ulam, Bradley, from some of these names. And that's how modern statistics took off. And now we have come to the 1950s, 1960s. Modern statistics is in place. Where do we use it? We use it in finance. We use it in statecraft. We use it in insurance, particularly, actuarial tables, things like that. I was at the launch of the Asian Institute of Insurance yesterday, and it's all statistics. Then something else happened, and this is where I think statisticians should have owned it, but a new field emerged, and that field is modern statistics. So modern statistics brings together mathematical statistics with things like graph theory, with things like topology, geometry, all these things come together. And modern statistics involves things like, of course, basic statistics, but things like data pre-processing and cleaning. How do you get rid of outliers? We have the statistical principles are there, but then you had to modernize them. In fact, one of my students, a group of my students started a company recently, I was on the board, called Clean Lab. They raised $25 million, and all they do is clean data for AI. Imagine if data is the fuel of the new economy, just like petrol is the fuel of the car. If the petrol has junk in it, it's going to clog up the engine. You need filters. So there's a whole industry now in cleaning data. And much of it is based on statistics, and much of it is based on modern theories related to unsupervised learning and clustering. And clustering is where the field of AI is separated from the field of statistics. And clustering algorithms are, things like regression, both linear and logistic regression. Things like decision trees, random forests. All of these things started emerging. Of course, some of the theory was known for decades, but it was only in the 90s, 20th century, early 20th century, that these things began to be used, because suddenly you had massive amounts of data and you had to look for patterns, and that is called unsupervised learning. And it's a form of machine learning, not neural networks, but it's a form of machine learning. Principal component analysis, for example, it was in the same neighborhood. Support vector machines, SVMs, K nearest neighbors, also called KNN. So the idea was that how do you find clusters? By the way, the early work in this started, although the field took off recently, in the 18th century when the typhoid epidemic was taking off. Statisticians used graphical representations to discover where the centers were of typhoid. And by the way, I've forgotten the name of the scientist. He discovered that it was the wells. It was the wells where typhoid was spreading from. And that's how they were able to control typhoid, by getting people to drink cleaner water, et cetera, et cetera. So that's an example of unsupervised learning. And this is where there was a separation between statisticians and modern data science. Now, another thing that happened around that time was computers started taking off and data storage started taking off. And this is an evolution of how data has grown in the last 10 years or 15 years, and how it will keep growing. Data is exploding. It is absolutely exploding. Every tweet, every text, everything you do is data. Every time you take a GPS location, that's data. Every time you take a photograph, that's data. The vast majority of data today is unstructured, not structured. Structured data is like Excel spreadsheets, but a photograph is data too. And I'll come back to that. This is the line that has been crossed in a way that is extraordinary between structured data and unstructured data. Statisticians deal with structured data. AI deals with unstructured data. We'll come to that. But data is exploding. What happened then was this happened, which is data started exploding. So data is going like this. Data is going like this. You can't really see it there. It's going like a rocket. But processor power is not growing so fast. It's growing fast, but it's not growing so fast. We thought that processing power would double every 18 months. It did. That's called Moore's law. It did. But we've made the lines on a chip so narrow, it's 3 nanometers now, that it's too narrow for electrons, basically. So the processing power isn't growing so fast, and the memory isn't growing so fast. So that's how the growth of data hit a wall. And everyone until then was working on computation. And so then a new field emerged. And that field is, and by the way, Moore's law is coming to an end, as I said. So this is the wall we hit. And we began to realize it about 25 years ago. And the way we dealt with it is a new field, and that field is data engineering. So data engineering is where engineers, computer scientists started working on, oh my God, how do we handle this data? So here's the problem. Your laptop, your computer, by the way, your phone today has more computing by orders of magnitude than all the computing on the Apollo moon mission, just so you know, right? That's how fast computation has gone up. But the old world, you put all the data on your computer. You will limit it to an Excel spreadsheet. And because computers are not growing fast enough to deal with the volumes of data, the new field had to be, how do you distribute the computing? And that is data engineering. And the basic idea there is that, let's see if this works. Can you advance the slide? Oh, there you go. Is we started doing a few things. First of all, we started going from, even before we had to do that, we realized that data has to live in silos. Okay, you had the ERP data, you had the HR data, you had the factory data, and you didn't mix them. If you mix them, you could discover things. For example, the quality went up when employee number 17 was in the factory. Then you could study what employee number 17 did and then make that quality improvement systemic. So these silos had to be brought together. And so it began in about the late 1980s, something called a data warehouse. Put all the data in a single warehouse, but still it was on a single computer. But then we realized the computer isn't big enough. So then we started creating the cloud, something called data lakes, data warehouses, and data lakes went to the cloud, and then something called data meshes and data fabrics. And this is how these massive storage and computing farms took off. And now in these computing farms, and you've seen pictures of this, right? That's where all the computation happens. And this is where Amazon, Google, Microsoft, Azure, for example, that's what they do. Now you can put the computation not on your laptop, you upload your data to the cloud. The cloud has thousands of what you call virtual machines, VMs, and these VMs is where the computation happens, and the data sits there as well, the storage sits there. And if you use Google in any way, you're using Apple, using iCloud or Gmail, you're in the cloud. So that's how we offloaded the data into the cloud. But that wasn't good enough. Then they had to figure out, how do you distribute the computing? And there's a thing called Hadoop, H-A-D-O-O-P. If you haven't heard of Hadoop, and if you're wondering where the name came from, it is named for a toy. The founder of Hadoop, the two engineers, one of them is a guy called Cutting, and his son used a toy called, an elephant called Hadoop. So he called it Hadoop. But it's based on an algorithm called MapReduce, which is a paper written by a guy called Sanjay Gamawat, my name, not me, MIT guy who's at Google. He wrote a paper called MapReduce. And the basic idea is, now what you do is you take a massive computation, which you would run on your computer, you would map it out, you put all the data in a very distributed cluster using something called HDFS, Hadoop file system, basically, Hadoop distributed file system. And then you took your computation, you split it up, you sprayed it out into this massive network of computers. They all did the compute. You had to figure out how to bring it all together because the data is too big to put in one place, the computer's too big. Then you shuffled and brought it back together, and out came your result. And that is Hadoop, and Hadoop is now an Apache project. Apache is an open source project. And now in data engineering, using Hadoop and clusters and cloud, this is how we were able to engineer our way around the wall we hit with the massive amounts of data, and that, of course, is data engineering. And data engineering and data science came together, data engineering and statistics came together and launched this field we now call data science. And by the way, I think statisticians missed a trick. Jeff Wu, who's an academic, gave a talk at the Chinese Academy about 20 years ago, and he said, we should really rebrand statistics as data science. And I still think it's not too late. I think we should. Because, as I said, I think that statisticians are the original inheritors of this legacy, and they should not lose that pole position. Okay, so with that, I will now jump into the next section, which is back to our map. So I've now told you how statistics and data engineering came together to create data science. Now let's talk about machine learning. Now, as I said, machine learning is not new. Machine learning is actually three fields. So you start with the data, so there's a lot of data. We already talked about it. machine learning is unsupervised learning. Unsupervised learning traditionally used to be things like clustering. But even that was mostly supervised. But the way I'd clarify, separate unsupervised and supervised learning is, supervised learning is when you give labeled data sets. Unsupervised learning is when you have unlabeled data sets. So you just have a massive corpus of data, right? So for supervised learning, you can't just give a picture of animals. You got to give a database with pictures of animals. For each picture, you've got to say, that's a dog, that's a cat, that's a raccoon, that's a tiger. And you have to give thousands, and that's how supervised learning happens. Supervised because a human being has to go and label them. And these data sets became very painful and difficult, and sometimes human beings would make errors. That's what my student's company, Clean Lab, does, which is clean up those errors. So that's supervised learning. Unsupervised learning is when you just give it a pile of stuff and it learns. And that is scary when that happens. If you can do unsupervised learning, that is terrifying. That's so powerful. And that's the era we're entering. Okay? So, if you look at the history of machine learning, next slide. Should I be pointing somewhere? Okay, let's just build it out, yeah. So, if you look at the history of machine learning, we've actually been through 3 waves in machine learning. The first wave began in the 1940s. Pitt and McCullough, they were the 2 scientists. They were both at the University of Chicago. They actually moved to MIT, where I also work. And then they created the first artificial neural networks. They put the neuron on a computer. And that wave, it started with a lot of hope and promise. That's the thing on the left. But it never really took off. And here's the reason why it didn't take off. Because the fact is that human beings overestimated computation. Let me ask you another question. Which animal do you think is more intelligent, a dog or a cat? Cat. Unfortunately, a dog has more neurons. I say this because my wife is a cat lover and she's very upset when I told her that. All right. Cats have 250 million neurons. Dogs have 540 million neurons. Now my question to you is, how many neurons do you think a human being has? What do you think? 86 billion neurons. 86 billion neurons. So somewhere between 500 million neurons and 86 billion neurons, Einstein, Malala Yousafzai, and Muhammad Yunus happen. Something magical happens. Early computation, early AI fell into the trap of not recognizing the majestic capabilities of the human brain. They thought, we'll just automate neurons, it'll work. Did not work. And finally, the field crashed. It nearly died. In fact, I did AI in 1992. I was doing research. I was too embarrassed to tell anyone because it became a stigma. It was a failed field. The second wave started in 2011. And the second wave began with deep neural networks, something called backpropagation, etc. There was first a paper using GPUs, graphic processing unit, by a guy called Kumar Chiplala. Then in 2011, there was a paper called AlexNet by Alex Stuyvesant, a whole bunch of people, Stuyvesant, and a whole bunch of people. And that's how the second wave took off. And that is what you use in face recognition, in Siri, voice recognition, Shazam, any AI that you see is that. And by the way, that wave is still very much alive and kicking. Self-driving cars use it. Anything, lane recognition in cars, all that is actually the second wave. The third wave started in 2022. That's when you got wind of it. I got wind of it in 2017. The first paper came out in 2017 from Google by a guy called, it's actually many authors, Vaswani et al., Ashish Vaswani et al., 2017, also Google. And they invented something called transformers. I'll tell you a couple of things about transformers. And that is large language models. So wave 2 and wave 3 are still continuing. They haven't come to an end. Both were made possible by large data, big data, and GPUs. But wave 3 is where a lot of our excitement is today, which is because of large language models. So we're in wave 3 now. But wave 2 is not dead. Wave 2 has a lot of life in it, and it will transform everything we know, right? So A lot of people say neural networks are just regression. I know statisticians, I know I grew up on regression, logistic regression, just linear regression, even nonlinear regression. And it is true that neural networks are a form of regression at some level. But one of the things that I think people don't realize is that neural networks, because of certain functions inside neural networks, like the arctangent, the sigmoid, and the ReLU, are a profoundly complete form of regression. And they're a highly nonlinear regression. In fact, you can think of neural networks as a way, when you do regression, you have to handcraft the features that you're regressing. You have to handcraft them. Neural networks, the incredible breakthrough is neural networks, you don't have to handcraft the features. It calculates the features and then does regression on them automatically. I'll give you an example. And this picture shows it. This is something from convolutional neural networks. The other day, there was someone was supposed to meet a friend of mine. He said, "What does he look like?" So I said, "Well, he's got a big nose." Right? That's a feature. I was recognizing that feature. But is that the optimal feature to recognize someone? Everyone in my family has big noses. It doesn't really count for much, right? The optimal way to recognize the feature is what neural networks do. So what they do is they take labeled data sets. So on the top, you have faces, cars, elephants, chairs. And then if you look at the middle section, it's actually identifying the most distinctive sub-features of a face, of an elephant, of a car, based on essentially statistical analysis of all faces. And then it's reducing them to even smaller sub-features. And so neural networks are a very advanced form of nonlinear regression where the features are not handcrafted. It recognizes the features. If I had to do this manually with regression, I would say length of nose and measure or something, right? But in this case, it recognizes the optimal set of features. And it does it entirely on its own. That's what makes it so powerful. So that's regression. And by the way, there are papers, one of them actually came from MIT, Tommy Poggio, that show that neural networks are a universal approximator. You can approximate anything with a neural network because they're so nonlinear. Any function, any continuous function can be approximated. And the other thing about neural networks is that unlike regular regression, which is so limited in scope, you can only do 2 or 3 regressions, right? They can do convolutional neural networks, recurrent neural network, and transformers. I mean, you can even do regression on language. That's how profound it is. And I'll talk about the regression of language next, and that is what large language models are. And then you can scale them using GPUs, Hadoop, which I mentioned earlier, cloud, and a whole bunch of other things. That's transfer learning, not transfer earning. I would love to transfer earning. That'd be a good way to make money. And then GPUs showed up. So all those kids you knew who play video games, right? They were actually driving an industry called GPUs, graphic processing units. And graphic processing units are made by a company called NVIDIA. Actually, my daughter did an internship there this summer. And NVIDIA creates these, and by sheer coincidence, NVIDIA's graphic processing units could do big vectors. Remember I said big vectors? And this whole business of interpolation is vector calculus. You know this, right? But the size of the vector is 1,000, 10,000. And what happened was NVIDIA, by coincidence, because they were doing graphics, developed these systems and they could solve linear algebra problems required for machine learning. They jumped into it. And today NVIDIA is one of the most highly valued companies on the planet. Jensen Huang, you've probably seen videos of Jensen Huang talking about it. And the reason they work so well is they do parallelization in 3 dimensions. One is data parallelization, something called pipeline parallelization, and something called model parallelization. And so what you can do with these NVIDIA Blackwell server farms, like the ones I showed you earlier, is you can take a massive data set and learn and interpolate with this nonlinear regression, and boom, you have created the ability to extrapolate, and that's what large language models are. Now, last thing I want to tell you is about word embeddings. And this is, in my view, somewhat profound and scary. So let me tell you what it is. The basic idea is, can you reduce a word to a vector? For example, can you reduce, this is a cat. Now, images you can reduce to vectors. Images are vectors. There are, 3 colors, and it's a square array. Boom, you can reduce to a vector. Every pixel is 3 vectors. And each pixel, if you line it up, you reduce it to a vector, no problem. But how do you reduce words to vectors? This is the breakthrough. And the way it happened was with some philosophical reasoning, analysis of something called analogical reasoning. This guy, Tikhon Mikolov, wrote the first papers on this. How do you reduce words to vectors? And it started with a philosophical question. You know, when we have exams, sometimes they ask you questions. A dog is to a puppy as a cat is to a dog is to a puppy, a cat is to a kitten, right? That's analogical reasoning. Human beings are very good at it. So they started with that question, king, queen, okay, gender change. Man, woman, gender, right? Or big, biggest. Small, smallest, extreme. So that's called analogical reasoning. They started with that. And then they started saying, let's assign vectors to words so that the vectors meet these constraints. So the vector, some number, some 1,536 dimensional vector for man and woman and king and queen, let's adjust them so that there's some transformation, linear transformation that makes this analogy work. And what they found is they can make it work. And that is what you see there. And let me tell you what that's actually a pretty extraordinary statement. Let me tell you what that's saying. If you take, this vector mapping is called word embeddings. Okay? So you can take any word and embed it as a vector. But here's the crazy thing. If you take the vector for king, you go king minus man plus woman, you'll get queen. Can you believe that? All our human language can be reduced to vectors. In fact, it's quite subtle. King minus man plus woman, you'll get not exactly queen, you'll come close to queen. You know why? Because queen has many meanings. In America, you have men who dress up like women. It's called a drag queen, right? You have the rock group Queen. By the way, Freddie Mercury is a relative of mine, right? So it's not exact. It's close. Right? I should say he's relative to my wife. But anyway, so king minus man plus woman is approximately queen. The fact that we could reduce human language to vectors suddenly meant you could do regression on language. And there's a whole range of embeddings. And you don't have to look at it all, but I'll just look at the top the top 2 categories. Context-independent vectors and context-dependent vectors. So until about 2016, even early 2017, all the word embeddings were context-independent. And then context embedding emerged, context-dependent emerged in 2017. Particularly something called transformers. And transformers are what created modern large language models, transformers. It's basically taking any word and seeing it in its context, giving it a vector, and the vector follows this calculus, interpolative calculus, that you can do regression, interpolation, extrapolation, and generative AI's extrapolation. That's basically what it is. And that, ladies and gentlemen, is going to transform everything we do. And just to give you a sense of why this is a national level project, this is like a nuclear project. In America, the private companies are big enough they can do it. Microsoft, OpenAI, Tesla, right? Google. But look at the size of parameters in billions. That is a supercomputer of a scale, but again, using distributed computing, data engineering, that we don't have access to in most parts of the world. India can do it, China can do it, Russia can do it. And so one of the challenges here is the advantage is very much on the side of the countries that can invest, because this interpolation is a nuclear effort, because you're talking about billions there. And MMLU is a benchmark. It's a massive multi-language unit. Anyway, it's a benchmark of performance. And GPT-4 just came out. We're talking about 1,300 billion numbers to capture GPT-4. And now they estimate humans. I actually don't, I think humans are much further, but they claim they're getting close to humans. But what I'll tell you is the impact on jobs is real. I think you know it. So the conclusion is this. We have breached many barriers with AI, and we are on the threshold of something incredible, scary, terrifying, and wonderful. Now, if you look at AI, if you look at old AI and new AI, let me just animate the whole thing. Used to be that the second wave of AI was about labeled data sets, supervised learning. Suddenly, we've entered the era of unsupervised learning. The second thing is, AI used to be about structured data. Do you know I said earlier, the vast majority of data today is unstructured. 80% of all data out there is unstructured. And this new large language models can get information from unstructured data. And you put the two together, and it's terrifying. This is a video. I didn't show you the video. There are now examples of robots looking at YouTube videos and learning how to do tasks. Let me repeat that. A robot looking at a YouTube video and learning how to do tasks. That is unstructured, unsupervised, sophisticated learning. Interpolation, extrapolation. What we did with words, we can now do with actions, and that's what robots are doing. And the impact is going to be staggering. I think Malaysia has maybe 5 years, because there are gigantic countries waiting to jump on this, investing, hungry people ready to jump in. If I'm the Philippines right now, I am terrified. A third of the national economy of the Philippines, the income, the remittance or the income comes from call centers and business process outsourcing. Game over. Today, I read, in fact, actually I read this a few months ago, but I was just looking at it this morning. A company called Klarna put out the following press release. So they built an AI assistant. It did 2/3 of all Klarna's customer service, 2.3 million conversation, chatbot. It replaced the work of 700 full-time agents. There was a 25% drop in repeat inquiries. That means they were able to take care of the customer more quickly. The resolution time dropped from 11 minutes to 2 minutes. It was able to operate in 23 markets, 24/7 in 35 languages. And it's estimated to drive $40 million USD revenue profit, not revenue, for Klarna in 2024. So this is the new world. Thank you for having me. This is just a sense of AI exposure to jobs. And I hope I've given you a mathematical basis and a historical basis for understanding where this is coming from. It's not hype. It's 80, 100, 300 years in the making. And all of that is coming together today. Thank you very much.
Thank you, Yang Berbahagia Professor Sanjay. Please remain on the stage for a moment. We would like to invite Yang Berbahagia, Datuk Sri Dr. Muhammad Uzair Mahidin, Chief Statistician Malaysia, to the stage to present the token of appreciation to Yang Berbahagia Professor Sanjay Sarma. Thank you, Yang Berbahagia Datuk Sri Dr. Muhammad Uzair and Yang Berbahagia Professor Sanjay Sarma. Ladies and gentlemen, we wish to cordially invite everyone to visit the scientific poster exhibition located at Conference Hall 2 and enjoy the refreshment at the pre-function area outside this auditorium. Please note that since the first forum session will begin at 11 a.m., we wish to seek your cooperation to be present in this auditorium by 10:50. Thank you.